Hey, everybody. It's Monday, April 19th. Hope you all had a nice weekend. As you can see here in the aim today, our goal for today's video is to pick right back up with our review for the AP test. And what I'd like to discuss in today's video is the problem that you were assigned over the weekend. Now, what you might have noticed about this problem, which is different from many of the problems that you've seen so far this year, is that there are just a ridiculous number of parts to this question. There's a reason for that, and that's because this problem was on the AP exam last year. And on last year's AP exam, they only had 2 questions, and so to try to get as much out of these 2 questions as they possibly could, they just made a million different parts to this question. That's okay, because like I said when I assigned this question has a lot of good parts that test valuable skills that you definitely need to have for the AP exam in its usual form, which I'm assuming will be the case this year, at least for those of you who are taking it in person. Let's just get into it. As I'm sure you remember, this question says a box is pressed against a horizontal spring, compressing the spring from its relaxed length. The box is then released, and the spring launches the box horizontally along a track that ends in a ramp, as shown above. The box has enough speed to leave the ramp, and the box reaches a maximum vertical height above the floor. Assume there is negligible friction between the box and the track, and air resistance is negligible. And of course, they give you the definition of all the terms used here in this diagram. The first part of the question says, the scenario is repeated now using a stiffer spring with a spring constant that has a greater value for K than that of the original spring. The stiffer spring is compressed the same distance x, and the same box is used. Part A of the question says, indicate how using a stiffer spring would affect the maximum height reached by the box, and explain why without mathematically deriving a relation for h. Now, the way I see it, and you could disagree, but the way I see it is there are 2 obvious ways that you could explain this based on equations that we know for a spring. You could start with the equation Fs, the force exerted by the spring, is equal to Kx, or you could use the equation, the elastic potential energy stored in the spring is equal to 1/2 kx squared. Now, what should be clear about both of these equations, because we have been doing this for a while, is that in both instances, you see the force is directly proportional to the spring constant, and the elastic potential energy is directly proportional to the spring constant. So a greater spring constant is going to mean the spring stores more energy, and the spring exerts a larger force on the box. Now, to me, and this is really where the opinion part comes in, to me, because they're asking you about the maximum height reached by the box, and height always comes back to energy, I think it makes more sense to explain this in terms of energy. That is just my opinion. And so what I wrote for this question is, if the spring constant of the spring increases, the spring will store more elastic potential energy when it is compressed a distance x. This means that when the block is launched, it will have a higher speed, which means when the block leaves the angled ramp, it will have a larger vertical velocity component, which will allow it to reach a larger height. If it starts with more energy, then when it reaches its maximum height, it'll have more energy, and that would be both kinetic energy and gravitational potential energy. And so if the spring has a larger spring constant, it will reach a larger height. Take a second to pause this video here and write this down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll take a look at the scoring guide. All right, so looking at the scoring guide here, this part was worth 2 points. The first point was for a statement that with the stiffer spring, the spring constant would increase, or the average force would increase, so the speed of the box as it leaves will be larger. Now, notice here, they talked about the force increasing. I think it makes sense to talk about energy, and saying more energy means more energy, whatever, but that's the basic idea. The second point is for a statement that says the speed of the because the speed of the box as it leaves the spring will be greater, the maximum height of the block will increase. And so for their example response here, they say a stiffer spring means that the spring constant is larger, which means that there is more initial energy stored in the spring, or that the average net force in the box is greater, which means that the launch speed is greater. So with everything else the same, the box will reach a larger maximum height. Take a second to pause this video here and make sure you fully understand all aspects of this scoring guide. And when you hit play, we'll move on to part B. All right, now part B has a question in it that they really have fallen in love with in the last bunch of years. And the reason why they have fallen in love with this question is because it really requires you to analyze equations. Now, I really go nuts about the equation analysis stuff in honors physics. You should definitely be able to tell looking at an equation whether things are proportional or inversely proportional or whatever, and how that's going to affect a quantity if you change something in the equation. And so this part should be pretty easy. It says students derive an equation for the maximum height h, and it says h is equal to sine squared theta kx squared over 2mg, which may or may not be correct. It says, is this equation consistent with your claim in part A? Why or why not? So obviously for this question, you have to think, well, what did we say in part A? In part A, we said a larger spring constant is going to yield a larger maximum height. So the obvious question here is, does this equation show a larger spring constant is going to give you a larger height? This equation shows the height is directly proportional to the spring constant. So a larger spring constant would yield a larger height. The answer to this question is yes. The equation is consistent with the answer to part A. The spring constant getting larger, that says the spring constant getting stiffer. It really should probably say the spring getting stiffer or the spring constant getting larger. The spring constant is a number, right? Numbers don't get stiffer. Anyway, the spring constant getting larger should cause the maximum height to increase, as we answered in part A. This equation shows the maximum height reached by the block being directly proportional to the spring constant of the spring, because it's in the numerator, right? Which means an increase in the spring constant would produce an increase in the height. Thus, the equation is consistent. Take a second to pause this video here and write that down, adding any parts of this explanation that may be missing from your own. And when you hit play, we'll move on to the scoring guide. So this part of the scoring guide says you get 1 point for indicating yes with an attempt at a justification using functional dependence, essentially by talking about how the equation shows proportionality. And the second point says 1 point is earned for indicating that since k is in the numerator, if k increases, h will increase. Now, I'm going to be totally honest here. I did not mention that part about it being in the numerator at first. I just said they're directly proportional, so if the thing increases, the other one's going to increase. They specifically use the phrase here because k is in the numerator. Now, I doubt they wouldn't have given you the point if you just said they're directly proportional, so if k increases, h increases. I don't really think you had to use the word numerator to get full credit here. But it is important to note, as we go through these problems, you want to look out for that in the scoring guide. The structure of the equation is key, and it literally costs nothing to just write parentheses and say it's in the numerator when something is directly proportional, or if they're inversely proportional, writing parentheses and saying it's in the denominator. That's an important thing to keep in mind as we go forward, because it's really going to piss me off, frankly, if you guys know exactly what you're talking about and you have the answer perfect and these bozos give you half the credit because you didn't use the word numerator, even though this stuff is like child's play to you. So just keep that in mind as we go forward. Maybe make a note for yourself and write that down. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. Moving on to part C here. Now, part C is the thing we've been training for our whole friggin' lives. Part C of this question, I think, is what we've always been looking at with these tippers questions, where they say these three kids, and the names are always an A name, a B name, and a C name, say this stuff. Who is right? Who is wrong? It's called a what's wrong task. We've done so many of these things. This is really where you should be scraping up every point. It is not always true, but 99 times out of 100, when they ask these questions, each kid says one thing right and one thing wrong. You will, from time to time, come to a question where the kid only says one thing right and nothing wrong, or only one wrong thing and nothing right. Having said that, 99 times out of 100, like I said, it's one thing right and one thing wrong. We're starting with student 1 for part C and D. Part C says which underlined phrase or phrases in student 1's statement are correct. If neither phrase is correct, write none. Now notice, I think this is important, it literally just says which underlined phrase or phrases. Notice nowhere here does it say explain. You literally just need to say which phrase. Now, I'm going to show my answer here, and I decided to do a little bit of explaining here because I'm trying to explain this stuff to you because I am your teacher, right? I wrote the student is correct in saying that the kinetic energy is a minimum at the maximum height. That's what the kid said, right? They said the speed of the block at its maximum height is 0 because the kinetic energy is a minimum at the top of the trajectory. The kinetic energy being a minimum at the top of the trajectory is true. Since the block rises after it leaves the ramp, it converts its kinetic energy into gravitational potential energy. This is going to sound stupid to some of you probably, but it does that. And by that, I mean converts its kinetic energy into gravitational potential energy. It does that until it doesn't anymore. And what I mean by that is it converts speed into height, essentially, converts kinetic energy into potential energy until it gets to its maximum height. And so because the kinetic energy gradually decreases until it reaches its maximum height, that's where it no longer converts kinetic energy to gravitational potential energy, and that's why it's a minimum. If you want to pause this and look at this explanation, you can. If you fully understand that, then let's just move on. Notice the scoring guide says for a correct statement and no incorrect statement. And notice here, not only could you have written student one is saying, student one is correct in saying blah, 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 and literally just quoting them. They let you get away here with just saying the second statement. Let's be clear. I am not advising you to do this. I think you should say student one is correct in saying, and then write what they said. But notice, no explanation here in these kind of questions. You just have to say what's wrong or what's right. In this case, it's what's right. Take a second to pause this video here and make sure you fully understand all aspects of the scoring guide. It's not that hard. And when you hit play, we'll move on to D. All right, part D says which underlined phrase or phrase in student one's statement are incorrect, if either. If neither phrase is incorrect, write none. Now, there's only one other underlined thing that the kid said, and that is that the speed of the block at its maximum height is 0. So the question here really is that correct or incorrect? It's incorrect. Look at the trajectory here. The trajectory is that of a projectile fired at an angle. At the maximum height, the object does not stop. Only one component of the velocity goes to 0. So what I wrote here is the student is incorrect in saying the speed of the block is 0 at the maximum height. Notice, that's the only thing. The bold part of that answer is the only thing you would have actually needed to say. I went on to explain it. At the maximum height, the block is still moving sideways, so it still has some non-zero speed. Remember the alligators. This is true because after the block leaves the ramp, it functions as a projectile fired at an angle. Horizontally, there are no forces acting on the block to slow it down, so it maintains, that should say maintains, I'll fix that in a second, it maintains a constant horizontal velocity component. It's unaffected by the force of gravity as it moves through the air. That's an important thing to realize here. The horizontal velocity is unaffected by the vertical forces because the motions in each direction are independent. These things don't stop at the max height when they're fired at an angle. Only the vertical velocity goes to 0. Again, if you want to write this down here, you can go ahead and pause here, but because there was no explanation required, I'm just going to zip to the scoring guide. Notice here the scoring guide just says 1 point for incorrect statements and no correct statements. You could have either said student 1 is incorrect in saying the speed of the block is 0 at the max height, or by just saying the first statement. Take a second to pause this video here and make sure you understand all aspects of that scoring guide. And when you hit play, we'll move on to the next part. Okay, moving on to part E here. Part E says which underlined phrase or phrases in student 2's statement are correct, if either. If neither phrase is correct, write none. Student 2 says only the vertical component of the velocity is 0 at the maximum height because the vertical component of the acceleration is 0 at the top of the trajectory. Which part of that is correct? The first part. The student is correct in saying that only the vertical component of the initial velocity is 0, right? We already sort of talked about this, but as the block rises, the only force acting on it is gravity, which acts straight down toward the ground. Since the force of gravity is opposite the vertical component of the initial launch velocity, the vertical component of the velocity decreases until the object reaches its maximum height. That's an important thing to realize here. These things being fired at an angle, only one component goes to 0. Again, you didn't have to explain this, so if you want to pause this and write that down, go ahead, but I'm just going to jump right into the scoring guide. The scoring guide, same thing, saying a correct thing and no incorrect statement, and there it is. Only the vertical component of the speed is 0 at the maximum height, or they would have let you get away with saying the first statement. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide, and when you hit play, we'll move on. All right, moving on to part F here for the last one of these. It says which underlined phrase or phrase in student 2's statement are incorrect. The only other thing they said that's underlined is the vertical component of the acceleration is 0 at the maximum height. Come on. That's ridiculous. The student is incorrect in saying the vertical component of the acceleration is 0 at the maximum height. Since the force of gravity acts on the object during the entire flight, The block always has a downward vertical acceleration of negative 9.8 meters per second squared. Come on, that's insane. The block wouldn't come down if there was no downward acceleration acting on it once it got to its maximum height. There's a force. Forces cause acceleration. Period, end of story. Again, if you want to pause this and write that down, go ahead. But as always here, the scoring guide is boring. It just says incorrect statements and no correct statements. And then there's the statement, vertical component of the acceleration is 0 at the top of the trajectory. Or you could have said the second thing. Take a second to pause this video and make sure you understand all aspects of that scoring guide. And when you hit play, we will move on to part G. All right, part G of this question here says, consider the system consisting of the box and the spring, but not Earth. How does the energy of the system when the spring is fully compressed compared to the energy of the system at the moment immediately before the box hits the ground? Justify your answer. Now, here's the big question that we always have to ask. If there's no Earth in the system, then what does that mean? I really want you to make sure you understand this, so I'll say it again. If there is no Earth included in the part of the system, then what does that mean? It means there's no gravitational potential energy. That makes the explanation slightly more complicated, but not the answer. Energy is conserved. This answer is a little much, so I want to go through it bit by bit. I wrote here, the total mechanical energy of the box spring system remains the same. When the spring is launched from ground level, all of the energy in the spring block system is elastic potential energy. That's just a fact. When the block is launched, that energy turns into the kinetic energy of the block. The second it hits that angled part of the ramp, gravity does work on it. Now, let's be clear. Because the Earth is not part of the system, technically the work that gravity does is external work on the system. But here's the deal. While it is true that gravity does negative work on the box as it rises, and it should be clear, the energy is decreasing. The gravity is slowing it down, right? And so that's why it's negative work, because negative work causes a decrease in energy. While it is true that gravity does negative work on the box as it rises, because it causes the kinetic energy to decrease, it does positive work on the box as the box comes back down from its maximum height. And that is, of course, because on the way down, the kinetic energy increases. The amount of work done on the way up and the way down is equal because the object comes back to the same height from which it was launched. Work is force times displacement, right? The upward and downward displacements have the same magnitude. And so the idea is, at this point, the box possesses a kinetic energy equal to the amount of elastic potential energy initially present in the spring because there is no external net work done on the box. Thus, the energy is conserved. This word net here is the whole ballgame. There absolutely is external work done on the box. Gravity slows the box down on the way up and speeds it up on the way down, but they cancel each other out. And so the total work over the whole trip up and trip down is 0. This, I think, fairly enough, is probably the most confusing part of this question. So take a second to pause this video here and write that down, adding any part of this explanation that may be missing from your own. And when you hit play, we'll move on. Moving on to the scoring guide here, this was a 3-pointer. You got 1 point for indicating the energy of the box spring system remains the same, basically just stating that the energy is conserved. You got 1 point for indicating that there is mechanical energy in the spring. Don't give up on these questions. Because notice, if you had no idea what the answer was and you just said the spring has spring energy in the beginning, you would have gotten a point. Notice the second point is for saying when the box lands, all the energy is kinetic and none is lost. You would have got points. And so notice their example response here says the energy of the spring the energy of the spring box system initially is spring potential energy. And just before the box lands, all the energy is kinetic energy. Because there's no network done by outside forces, the energy of the spring box system is the same. That's the key idea. Notice there is another example response. Take a second to pause this video here and make sure you understand all aspects of this scoring guide, what they're giving you all the points for here. And when you hit play, we'll move on to the second to last part here. All right, second to last part here, part H. It says if the friction between the track and the box were not negligible, state one way in which the setup could be changed such that the maximum height of the box would be the same as in the original setup. Now, I actually want to go back to the picture of the original setup. I didn't write an answer to this one because, as you'll see when we look at the scoring guide, there are a bunch of different answers for this one. If there's friction here, that just means the speed that the box has right here is going to be smaller because friction is going to take away some of that kinetic energy. If the box is going slower, but you want to make the height the same, there are a couple of things that you could do. Honestly, what I first thought of, and I didn't really think about it that hard, it was just the first thing that popped into my mind. I said, well, the vertical velocity is going to be V naught sine theta. And so if the V naught value goes down, I can keep V naught y the same if I just increase the angle, make the ramp steeper. Yeah, it'll have less horizontal velocity, and so it's not going to go quite as far, but that's fine. I just got to keep the height the same. In my opinion, there are more obvious things you can say for this question, and so I didn't write an answer. I didn't want to be, not transparent about what I first thought when I was looking at this, and so I figure I'll just show the scoring guide. You get 1 point here if you say making the ramp steeper, trading out the spring for a larger spring constant spring, using a box of less mass. So here, notice they say you could increase the compression distance. That's the real answer given down here. Make the ramp steeper, larger spring constant spring, less massive box. All of those make sense. And notice here, I want to just go back to the question, the word state means what you think it means. They just mean say it. You don't have to explain it. They did explain it, but it says for a valid change that could be made, so the maximum height of the box would be the same. That's it. Non-negligible friction would cause the mechanical energy to be dissipated. Therefore, the compression distance could be increased so that the spring transfers more energy to the box, offsetting the loss in energy from friction. That's the basic idea. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, last part of this question, a nice question, I think. It says the graph below shows the horizontal component of the displacement of the box as a function of time. The graph represents the entire time the box is in the air after the box is launched from the ramp at an angle theta to the horizontal. The question says, how would the slope of the graph be different, if at all, if the angle were larger than theta, but less than 90 degrees, and the height of the end of the ramp were the same? Justify your response. Now, I would hope it makes some good common sense here to you that in order for you to really figure out how the slope of the graph would be different, that you figure out what the slope of the graph is. This is a graph of horizontal displacement measured in meters versus time. And so the units of the slope are units meters per second. That doesn't help you out as much as you need to be helped out, though. It's important to realize here that horizontal displacement over time is an equation for something. And it's an equation for the x velocity. Notice when we usually use this equation, we have it solved for the range. But nonetheless, you take that and you put delta x over t, you get Vx. So it's very important to realize what this question is asking you is if we increase the angle, what's going to happen to Vx? It is sort of cloaked in this how would the slope change thing. But since the slope is the horizontal component of the velocity, they're really just saying if theta changes, how is Vx going to change? And what I wrote here is the slope would be smaller. The slope of the line on this graph has units of meters per second. Since the y-axis value is the horizontal displacement, delta x, and the x-axis value is time, t, the slope's value is delta x over t. Since the horizontal displacement divided by the time is the horizontal component of the velocity, the slope represents the horizontal component of the velocity. Since the horizontal component of the velocity is given by the equation Vx equals V naught cosine theta, the increase in the angle causes a decrease in the cosine of the angle, which would decrease the horizontal component of the velocity. It's more vertical, less horizontal. That's it. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the scoring guide. All right, now just jumping very quickly to the scoring guide. Scoring guide here says 1 point for indicating the slope of the line would be smaller. 1 point for indicating that with a larger angle, the horizontal component of the initial velocity is smaller. And then 1 point for indicating the slope of the horizontal position as a function of time graph is equal to the horizontal velocity of the box. So their example response says, since the graph is of horizontal position as a function of time, the slope of the line represents the horizontal velocity as a function of time. Notice in their answer and mine, the key thing you need to recognize first is if they're asking you what's going to happen to the slope, it's a smart idea to establish what the slope is. Then they said if the box were launched at a larger angle, the horizontal component of the velocity would be smaller. And so this line would start at 0 still, but would have a smaller but still positive slope. And with that, that's it for this question. I liked it. It's a nice question. You'll probably notice, or you will probably have noticed if you paid attention to the Google Classroom page, there is no free response question assigned for today. That's because there is a simple harmonic motion homework assignment for tonight, as well as another video about the activity I asked you to do with that simulator last week. And I think 2 videos and a homework assignment is plenty of work for today. And so make sure you check out that other video about that simulator activity. I like that question as well. And we'll pick back up with those free response questions again tomorrow. All right, everybody. Have a good one. Watch that other video.